So in this equation, just referring to the particular solution, when we are operating at lower frequency, that means R is less than 0, means near to 0, that our structure should be designed in terms of stiffness control. So we have to provide a material with good stiffness. Okay. And another case is when it is operating in higher frequency, that means omega over omega r, omega n greater than 1, means too much greater than 1, then it is mass control design. And another is if it is operating near to resonance, that means we have to provide some damping material. Material with good damping property. Okay, so that is what we can conclude from the above. Frequency of maximum amplitude, the solution becomes x is equal to f naught over k. Actually, this is a similar solution. It is not as such different. F naught over k over radical of this minus 1 over 2 means our radical is downward, so we can bring it to this equation. So it is similar. So x bar is the maximum amplitude when d over dr of x is equal to 0. So how we can do that? X is maximum. That means the way how we can find maximum amplitude. When r is equals to omega over omega n, which is equal to radical of 1 minus 2 zeta square, which is called resonance frequency. Okay. Then omega of resonance is equals to omega n, that means the natural frequency times 1 minus 2 zeta square. So this is the resonance frequency that we can compute. So let's consider some rotating unbalance. One of the case for mechanical vibration of the system is the eccentric mass, which is situated in somewhere at some eccentric distance from center of rotation. Look, this is, you can consider clothes washing machine. In clothes washing machine, which is operating in the, which provide rotary motion, if there is some small mass, eccentric mass in the structure, that is one of the source of vibration. Okay, so rotating unbalance is the source of vibration. So look, this is a small mass placed at e distance from center of rotation. This is the center of rotation. So this disk is fully rotating. There is big mass of the system, and this is a small mass which is rotate with the whole system. What it produces? It easily produces the centrifugal force, me omega square. That means mass times centripetal acceleration or centrifugal acceleration. And when you resolve this force into x and y, you can find in the x me omega square cos omega t. This is the forcing frequency. Omega t is the forcing frequency. And the y component is me omega square sine omega t. Look, this is me omega square sine omega t. So it is the component of this force in the vertical direction. And this omega is the rotational speed of the motor or the machine. Okay. E is the eccentricity, and m is small mass, not the bigger mass. Bigger mass is the mass of the whole system. Okay, it is different. So now, just you can cut this system from here. If you cut this system from here, you can find free body diagram of this system. So from that free body diagram, you can easily get m capital M represents the whole mass of the system, the structural mass. Okay, so M of the rotating mass times x dot dot is acceleration. Okay, plus Cx dot plus Kx. That means this structure vibrates in this direction. Look, it vibrates about this position, up and down, so that you can cut this section and you can put an appropriate free body diagram. From that free body diagram, it is forcing due to this centrifugal force. Okay? This is the excitation force now. Me omega square sine omega t, because this sine omega t is in the vertical direction. The horizontal component has no relation with this force. Okay, so you have this kx force in this direction. Again, let me put bigger mass here, bigger mass, M capital here. Again, you have this thing, what we call C times x dot, and acceleration is here, x dot dot, double dot, and the component of centrifugal force acting in the vertical direction is me omega square sine omega t, Yeah, so just take this free body diagram and represent your this thing. So it is just mx dot dot plus cx dot plus kx is equal to me omega square sine omega t. Now this is the f of t, the forcing frequency or the forcing which leads to non-homogeneity or non-homogeneous second order differential equation. So this is f of t component. Now, for such case, the solution, we can consider particular solution as we have discussed before here. The particular solution is this one. This is the complementary solution for this case. That means this solution is the solution for mx dot dot plus cx dot plus kx is equal to 0. For that, we have this solution. And for the forcing function with sign condition now, it is with sign. So we can consider sign here, x bar times, instead of e the power of j omega t, we substitute sine omega nt. We can substitute sine omega t here. Okay. So by doing that, we can find this is the f naught. F naught in this equation is what? Look here, f naught is me omega square. Me omega square is f naught. Okay. So instead of f naught, you can put me omega square, and this k is taken from the bottom, so that k is there. Okay. Previously, it was f naught over k. Now, instead of f naught, you have me omega square. Just put it here. And then now, what is there? We have m here, we have k here. So, radical of, you know this equation. Yeah. You know, omega n square is equals to radical, or omega n square is equals to k over m. So you can bring this m down here. So it becomes k over m. So which is omega n square. So omega m, this m is come here so that it becomes r square. Yeah, r square is from that. Again, there is me. Okay, 1 minus r square. This is correct. Plus 2 zeta r, the whole square, correct. Me over k. So let's bring m, capital M from the equation and a small m. So it comes like that. So this is just, yeah. Actually, it should be like this. This should be E times r square, E times r square over this quantity, according to my observation. Okay, we have 1 minus r square, the whole square, plus 2 zeta r. Okay, 2 zeta r, the whole square, and the radical. So this mt and m come here, so that have some kind of problem. So let's consider it is just e r square. R means frequency ratio. E r square over radical of 1 minus r square, the whole square, plus 2 zeta r, the whole square. And the pi value is this component divided by this component, so which is 2 zeta r, the tan inverse of 2 zeta r over 1 minus r square. So the float of x and pi are given here. Okay, that, yeah, this is the float. Actually, this is displacement transmissibility and force transmissibility. So the float is not given here. We can see this float again. So that float is known as transmissibility. Okay, FTR over F naught. Anyways, so if the deflection of foundation is negligible, then the force transmit to the foundation. Actually, yeah, this is the case. This is another case also. The base vibration condition. This is Martian vibration. Another case, base vibration will be there. Okay, in this case, the transmissibility is from Martian to base down. But another case, there is base is a kind of vibrating base. Okay? Base is vibrating. That means kind of sinusoidal vibration of base is there. So during base vibration, we can put the free body diagram like this. Okay, the base vibration is considered as the point where the structural vibration will take place. So during that time, we can take such kind of free body diagram. So on that, we have Y, which is the base vibration, X is the system vibration. So the resultant of vibration is X minus Y. And X dot minus Y dot is the velocity resultant. So mx dot dot plus c times x dot minus y dot plus k times x minus y is equal to 0. So we have now nonlinear kind of equation in terms of x and y. How we can solve that kind of vibration? So you can bring this c times y dot to back, k times y to back. Okay. Now y is known. Y of t is equal to 1 sine omega t. Okay, y of t, this y is equals to y sine omega t. Again, y dot is y times omega cos omega t. So look, these are here. Mx dot dot plus cx dot plus kx is equal to ky sine omega t, ky sine omega t plus cwy cos omega t. So this quantity means this part is in general represented as a sine omega t. This a is radical of ky square plus cwy square. Okay, means we are just using this is not minus, but it is plus. Means what we are looking is the maximum amplitude condition. This square plus this square will give us a. Means a is equals to radical of yk the whole square plus cw of y the whole square. So if you take y out, it becomes a is equals to y times the radical of k square plus cw the whole square. And alpha here, this alpha is defined as tan inverse of cw over k. Cw over k means cwy over ky. So y by y, so we have left cw, it is with minus actually. Yeah, alpha is represented as minus here, so it is minus. Now, this is the equation. So it is what? Mx dot dot plus cx dot plus kx, which is equal to a sine omega t minus alpha. Now, let's consider the harmonic motion, because this is harmonic sine function. So x of t is equals to x sine omega t. Now, for such case, what is our equation before? The equation we derived in the previous case is what? X is equals to f naught. In this case, our f naught is a. Okay, f naught over k the whole over radical of 1 minus r square the whole square plus cw as the 2 zeta r the whole square is the previous equation. So now instead of f naught we have a, so you can substitute a here. What is a? A means this equation. Instead of f naught, just substitute y times radical of k square plus cw square is the a value over simply k. But there is k down, so we don't want to bring k here. It is there. If we bring k here, this becomes 1 and this becomes 2 zeta r. Okay, so this is k square plus cw square, that is f naught times y. Why we bring y here? Y is here initially, so it came here. Now x over y is the transmissibility or the displacement transmissibility. እየተረዳችሁ ነው ግን? በደንብ እዩት። ያቺ ኤፍ ኖት የምንላት ቦታ ላይ ኤ ሳብስቲቲዩት ስናደርገው ኤ ደግሞ ምን ብለናል? የኬዋይ ስኩዌር ፕላስ ሲደብሊው ስኩዌር አንደር ራዲካል ነው ፓይታጎረስ ቴረም ማለት ነው። ሳይን እና ኮስ ምንድነው በ90 ዲግሪ ዲፍረንስ ስለሆነ one is perpendicular to another and the resultant of the two amplitudes ky and cwy የሁለቱ ሪዛልታንቱ ደግሞ የሚሰጠን ምንድነው maximum amplitude ነው። so that a is simply y times y square times k square plus y square times cw the whole square እና ያን ደግሞ k ከዚህ ውስጥ ሲወጣ just take out k from here, just put k here, then k square 1 cw over k the whole square ማለት ደግሞ 2 zeta r ነው። እዚህ ጋርም cw over k 2 zeta r ነው። ስለዚህ ይሄ ይመጣል። this is the simplified representation and this representation is known as displacement transmissibility. So how the displacement transmissibility works this is the transmissibility x over y and this is the frequency ratio. Okay, frequency ratio 1 like maximum amplitude resonance condition now, then radical 2 ሲሆን ምንድነው የሚሆነው? Okay, this is point where radical 2. So on that zeta is 1 in the critical damping condition. For zeta very small, for zeta increasing and for zeta critical we have this kind of diagram, or this is the displacement transmissibility versus frequency ratio diagram for base vibration. This is in the case of base vibration. Don't forget what we are talking is the base vibration. Again, the phase angle pi versus the frequency ratio is presented in this diagram. So you can see various regions with various results, and this easily be plotted with the help of MATLAB. Okay, so another example is reciprocating machines, that piston cylinder mechanism. You see, there is base here, and this is situated on the base with base is fixed to both ends, and this machine is moving the cylinder and piston mechanism. It rotates about this point and reciprocates in this axis. Okay, so what we are going to find is find the amplitude of vibration for the plate. So how this plate is vibrating. Okay, so this is machine base now ማለት ነው። ማሽኑ reciprocate when about this axis rotate ያደርጋል, about this point it reciprocates because this is reciprocating pump having weight of 68 kilogram, which is mounted at the middle of steel plate with thickness 10 millimeter with 500 millimeter width and 2.5 meter length, which is clamped along two edges. And during operation, the plate is subject to harmonic force. Look, the force also given as harmonic force of F naught is equals to 220 cos 62.832 T. This is omega. Even here, look, F naught is given, omega is given, forcing frequency, that is 62.832. And the material's youngest modulus, which is 200 gigapascal, is given. So everything is given, yes. So how we can solve it? We have to calculate the stiffness of this material from the strength of material concept. So from the strength of material concept, the stiffness of this material is K is equals to 192 EI. EI is the rigidity modulus, or the rigidity of the material. So E is the youngest modulus, I is the second what we call that inertia, second inertia that have 1 over 12. For rectangular object, it is 1/12 BHQ. Okay, so this is the rigidity modulus. Okay, over LQ. This is directly from strength of material course. Okay, from that we can easily find the stiffness of material. So the stiffness of material for the given material system is 102,400.82, and the maximum amplitude of X is found as X is equal to F naught over K over M omega square. So from that we can find minus 1.3248. So this negative indicates that the response is out of phase with excitation. Okay, yeah. Another example is find the total response of single degree of freedom system with mass this with viscous damper 20 Newton second per meter, stiffness 400 Newton per meter. Initial condition X naught is 0.01 meter, X naught dot is 0. When external force F of T is equal to F naught cos omega T acts on the system. So let's hello? Yes?
Hello?
Yeah.
Ikarta doctor, Zintan Brobino.
Huh?
Zintan Brobino, Ikarta doctor.
Okay. So this is the second example. So this is harmonically exciting system with the harmonic force F naught cos omega T. So F naught is given 100 and omega is 10 rad. So immediately we can find what is omega n. So just calculate omega n. Omega n is equal to radical of K over M. From that you can find K is given, mass is given, so it is 20 rad per second. Then the damping ratio zeta is equal to C over Cc. C over Cc. Cc means critical damping coefficient. So Cc is 2m omega n. So that C over 2m omega n gives you 0.05. That is the damping coefficient. Okay, no, the damping ratio. And then the damped natural frequency is calculated from undamped natural frequency. So the damped natural frequency omega is equals to radical of 1 minus zeta square omega n. So omega n is already calculated from here. Just substitute it. Then you can find, and zeta is also calculated. So which gives you 19.975 rad per second. And the frequency ratio, which is equals to omega over omega n. This frequency ratio is the forcing frequency, which is given 10 rad per second, divided by the natural frequency, which is obtained from the material stiffness and the material mass, okay, which gives you the damping ratio is 0.5. So let me ask you one question. Now, our damping ratio, no, the frequency ratio is 0.5. Does this system, the mass control system or stiffness control system? Hello? Anyone can answer this? Look, the forcing frequency is less than the natural frequency of the system. And now it gives us the damping ratio, no, the frequency ratio is equals to 0.5. So what do you suggest for your mechanical design? Is it stiffness control, mass control, or damping control?
I think it's mass control.
Is it? Whenever the damping, whenever the R value is less than 1, we consider the stiffness control system. And if it is greater than 1, we consider mass control. If it is exactly equal to 1, the damper control system should be come to our mind. So this is just a stiffness control system. We have to
Again,
suggest stiffness
so
control or material with
question.
good stiffness.
ጥያቄ ነበር
So now
ይሰማል?
let's go to solution. Once we obtain these parameters, then the solution is very
ዶክተር ኪሩቤል
Yeah,
ጥያቄ
hello?
አለኝ እያለ ነው። ኪሩቤል
አይ
ጥያቄ
ጥያቄ
አለኝ
ነበረኝ።
እያለ ነው።
አይሰማም እንዴ ድምጽ?
ምን ነበረ?
አይ ኩዌስችን ነበረኝ። ጀስት ሌዛን ዜሮ ስለሆነ ነው ኦር ዜሮ አካባቢ የሆነ ትንሽ የፍሪኩዌንሲ ስለሆነ ነው ስቲፍነስ ኮንትሮል እንደሚሆነው?
እሺ ኩዌስችኑ ምንድነው?
ማለት ቅድም ያገኘነው አር ሌዛን ዜሮ ማነው ሌዛን ዋን ስለሆነ ነው ወይስ ዜሮ አካባቢ ያሉ በሁለቱም ዳይሬክሽን ስለሆነ ነው? በሁለቱም ዳይሬክሽን
ሌዛን ዋን በሚሆንበት ጊዜ
Between
ከዜሮ
zero and
እስከ
one
አንድ
ማለት ነው።
ባለው ሬንጅ ላይ አር ቫሊው
ኦኬ
የፍሪኩዌንሲ ሬሽዮ ከዜሮ እስከ አንድ ባለው ሬንጅ ውስጥ ባለው አፕሮፕሪየትሊ የስቲፍነስ ኮንትሮል ወይም ደግሞ ማቴሪያል ዊዝ ጉድ ስቲፍነስ ቢሄቪየር ያለውን ነው ሰሌክት የምናደርገው። The next near to resonance region ምንድነው የምናደርገው? ዳምፐር ኮንትሮል ነው። ዳምፐር ነው ወይም ዳምፐር should be introduced into the mechanical system in order to avoid the resonance effect. Okay, so that may be 0.75 up to 1.25 ባለው ሬንጅ ውስጥ ዳምፐር ብንጠቀም የተሻለ ይመስላል። Then after, if it is far away from one, then mass control. አሁን ለምሳሌ ብዙውን ጊዜ ትላልቅ ህንፃዎች ላይ unnecessary huge mass እናስቀምጣለን። Even in case ይሄ ሲስሚክ ኮንዲሽን ወይም ደግሞ ይሄ ኤርዝኩዌክ እንኳን ቢመጣ የስትራክቸሩን ሆልድ ማድረግ የሚያስችል ማስ ይሰቀላል ወይም ደግሞ ሪዳንዳንት ማስ ይቀመጣል። That is for the condition for higher external frequency. To overcome higher external frequency, we need some kind of excessive mass. To overcome lower external frequency, we introduce good dumb and good stiffer material. And at the point where resonance is expectedly occur, we consider the damping material is good damping coefficient. Okay, so this is the way how we can identify, especially in the critical region. Critical region means that R is equals to 1, again zeta value less. That means we are on the way to have kind of resonance. So damper should be applicable to avoid a resonance condition. So understand Argenia?
Yeah, it's clear.
Yeah. So now in the solution, the static deflection is F naught over K. So you can put the static deflection here. Now, X bar, the general solution for the not general solution, but the particular solution X is equals to F naught over K or delta ST over radical of 1 minus R square the whole square plus 2 zeta R the whole square. So we know R value, we know delta value, we know zeta value, so that substitute, and finally you can get the maximum deflection or the maximum amplitude of vibration in the particular solution case is 0.3326 meter. And the phase angle is just substitute values of those constants, and finally 3.814 degree is the pi value. And then the total solution is x of t is equal to xc, x complementary plus x particular. Okay, so the x complementary is just a e raised to zeta omega nt the whole times omega nt plus psi or some pi, that is phase angle. Okay, and then plus x bar cos omega t minus this is the pi value, okay. Now substituting these values, appropriately what is the damped frequency. This is natural frequency. Another is damped frequency. No, this one should be the damped frequency. Okay, omega dt. Omega dt is calculated as 19.975, and omega n is calculated as 20. So this is omega n. This is omega d. So omega d is 19.9470 minus psi. This is x is already calculated from here. X is equal to 0.326. Just substitute x here. All parameters are introduced. Now what is left to find A? A is the parameter. We have given initial condition here. What was the initial? X naught dot is equal to 0. X naught is equal to 0.01. So that means at time t0. So at time t is equal to 0, x of t is equal to 0.01 meter. So substitute on the equation. Hello?
አንድ ደቂቃ ነው የቀረውን።
Yeah, okay, we can summarize this point. So እንደዛ በማድረግ ምንድነው የምናገኘው? A cos psi which is equal to 0.33187 እናገኛለን። እንደገና ደግሞ x of t ቦታ በመተካት t is equal to 0, x dot of t is equal to 0 በሚለው እንደገና ሌላ ኢኩዌሽን እናገኛለን። አሁን ሁለት አናውን ነው ሳይን አናቅም ኤን አናቅም። ለዛ ነው ሁለት ኢኩዌሽን የሚያስፈልጋል። ሶ a sin psi is equals to minus of 0.0219 እዚህ ጋር አገኘን። እዚህ ጋር ደግሞ